Okay, we're going to look at a few different examples here. This is just kind of a review. The first one says that if this was a graph of f, so let's put an f there, then where are the inflection points? Now we want to point out first that this part is concave down, and so is this part right here. And in the middle, our original function is concave up, because we're looking at the original function f. So where are the inflection points? Should be obvious. It's going to be point B and point D. Now I want to point out that A, E, and H are all just zeros. Okay, now we're going to take this exact same graph and pretend that it was f prime. Okay, if that same graph was f prime instead of f, then that means we're looking at the derivative, and we have to use that to explain what's happening with the original function. Again, we're still looking for the inflection points. So what we want to know is, we want to know where is the second derivative changing signs. Now, how do we find the second derivative if all we have is the first derivative? Well, we're going to have to do one more derivative. So what I'm saying here is the derivative of f prime is going to equal f double prime. And that's what I'm looking for, f double prime. Also, another way of saying derivative is just saying slope. So the slope of f prime will give us f double prime. So we need the slope of this graph, and that will be the second derivative. You can see that the slope is going to be positive here and positive here. You can see the slope is going to be negative here and also over here. So the pluses is where our original function is concave up, and the minuses are where our original function is concave down. Again, we're looking for inflection points. So anywhere those pluses change to minuses, or vice versa, you're going to have an inflection point. So we're going to have an inflection point at A. F also has an inflection point at C, and F has an inflection point at G. So those are the three inflection points for F. Now, what if this graph was F double prime? If this graph was F double prime, then our inflection points for F would occur where our second derivative changed from either positive to negative or from negative to positive. And remember, this is f double prime, so to be positive, you have to be above the x-axis. So this is where f double prime is positive, because that's where f double prime is above the x-axis. F double prime is negative when f double prime is below the x-axis. So this is where f double prime is negative. And of course, the second derivative is going to be 0 at these three spots. So the second derivative is going to be negative when it's below the x-axis. So that's all the yellow part. And the second derivative is going to be positive when it's above the x-axis. So those pluses and those minuses are the polarity of the second derivative, so either positive or negative. Remember, to have an inflection point, you have to change either from positive to negative or from negative to positive. That does not happen at A, so I'm going to say no for A, but it does happen at E, and it also happens at H. So our two inflection points for F occur at x equals E and x equals H. Okay, for this example, it says that the graph of F is shown to the right. So which of these graphs below could be the graph of F prime? So they give us F, and we have to find F prime. Now, I do want to point out that this does look like an x to the third function. Because it's pointing down in the end, I'm going to say it's some kind of negative x to the third function. Now, because it does have this bump in it, it goes down, it comes up, and comes back down. There's going to be some other pieces like plus x squared, minus x, and all that kind of stuff. But basically, it's an x to the third function with a negative in the front. And if you know that from pre-calculus, then you know that the derivative would have to be some kind of negative x squared function. So I would just choose A right away, because A looks like some kind of negative x squared function. Now, some people would say that that's cheating a little bit, but if you're taking an AP test, whatever you can do to save yourself time can become really, really valuable. Now let's go ahead and do it the slow way. Again, we're starting with F, and we're trying to find F prime. Remember, F prime is the slope. So what we're looking for is something that is negative, because the slope is negative, until you get to -2. This is x equals -2. Then we're looking for something that is positive because the slope of this graph is positive until you get to this spot here. It looks like 1 point something. Again, we have f, we're looking for f prime. So we're looking for the slope of this graph. And the slope of this graph is negative after that spot. So again, f prime should be negative, then positive, and then negative. Now I do want you to notice that c is negative, then positive, then negative. And the same thing with a. A is negative, then positive, and then negative again. However, the spot where the f prime changes is different for those. We're supposed to change at -2. For letter A, it does change at -2, but for letter C, it changes at 0. Also, we're supposed to change from positive to negative at 1 point something. Over here on letter C, it changes at 2 point something. On letter A, it does change at 1 point something. So definitely A is going to be the correct answer. Okay, here they give us the graph of f prime, and they want to know some stuff about f. So what's bigger, f of E or f of B? If you want to compare those two things. Now remember, we're looking at the slope of f. Because we're above the x-axis over here, then f is going to be increasing all the way until you get to B. Then f is going to be increasing again all the way till you get to E. I want you to notice that f prime is positive all the way until you get to E. Of course, the derivative is equal to 0 at x equals b. But basically that means that the original function goes up, and then it continues to go up again all the way till you get to E. Then when you get to E, you'll notice the first derivative is negative because the graph is below the x-axis. So that means the original function is going to be decreasing. So we're going to be decreasing after E. So what is bigger, f of E or f of B? Well, f of B is going to have this height right here, and f of E is going to have this height right here. So we're going to say yes to question 1. F of E is greater than f of B. Okay, for question 2, is f concave up from A to B? So what we need to know what is the second derivative from A to B. Remember, the second derivative is the derivative of the first derivative. And so we just need to find the slope of the first derivative from A to B. The slope is negative, so that means the second derivative is negative. So we are concave down from A to B. So we would have to say no to question number 2. Okay, question 3 asks if f has a relative minimum at x equals E. Now, because our first derivative is positive from D to E, that means our original function is going to increase from D to E. Then our first derivative is negative afterwards, and that's because the graph is below the x-axis. Since our first derivative is negative, that means our original function f would be decreasing after E. So it looks like point E is going to be a relative maximum. So we're going to have to say no to question number 3. Okay, this last one's just a review question. We want to use linear approximation to estimate the fourth root of 17. If we let our function equal the fourth root of x, we can use an easy point. When x is 16, the y is going to be 2. Remember, this is a fourth root function, so it only has one answer. It's not a real fourth root. Now we just need the slope in order to do the equation of a line. I'm going to rewrite my function as x to the power of 1/4. And when I do the derivative, the 1/4 comes down, and the new power is 1 less. Okay, I found y prime of x, but I need y prime of 16. Fourth root of 16 is just going to be 2. 2 to the third is 8. So I get 1/32 for the slope. Now we can do the equation of our tangent line. Add 2 to both sides. And now we can use this tangent line to approximate the fourth root of x function when x is 17. So our estimate ends up equaling 65/32. Let's see how close that is to the real value. That's what we got for our estimate. And this is what the calculator tells us for the real value of the fourth root of 17. It looks like we were accurate up to 2 decimals. If this was a real AP test question, They might let you use the graphing calculator. However, if you put 2.030, you would get the question wrong because they're asking you to use linear approximation to estimate it. So our answer with 3 decimals of accuracy would be 2.031.